Thanks for joining us for this month's SMD live event, which today we're going to talk about shallow floor deck construction details. You will have seen we have done this one before. There are a few new slides added, but welcome to anyone who's sort of signing in for the first time. Feel free to take any screenshots as we go through. There will be links to our TGN online, so it can sometimes be useful. Pete will also put links in if you ask questions into the chat as we go. So just from a starting point of view, explain where you can find the information, or a lot of the information that we're going to talk about today is contained within a number of documentation that we've been involved with and our own documentation as well. So the one on the left is our SMD technical guidance notes. That's our basically go-to for everything we do in terms of it's our technical content, it's how we respond to queries. A lot of the information is contained in there, and lots of what you'll see today, imagery, can be found in there and content about it. The other two documents are documents that we've been on the working group for, so we've contributed to best practice guides, the orange or yellowy orange one being the SCI P300 document. That's the best practice for composite slabs and beams using steel decking. The right hand one, which is TR75 by the Concrete Society, is more about pouring concrete on upper floor decks and how that differs than doing it at ground floor, and also the design considerations you need to think about when designing composite slabs, upper floor decks, rather than the considerations that you may make at ground floor. So just useful references and go-to points for you in the future. The TGN document I showed you on the left there is also available in TGN online. So it's a wiki site. It's got loads of information and lots of what you'll see today, plus a load more. And we use that to answer technical queries and hopefully to allow engineers, specifiers, customers to answer their own queries as well by registering on our website and using that portal. In terms of today's CPD, I'm going to go through some details specifically relating to our shallow floor deck profiles and composite beam details in relation to our products. We're going to start with supports and fixings, so typical support types, what fixings we would then use on those different supports. We'll then go on to slab edges, edge trims, and how you form those slab edges and some of the limitations involved. The third section will be on shear studs and then flashings to facilitate shear studs through the deck onto the beams. Onto section 4 will be voids and VoidSafe. So VoidSafe is our void protection system that we install as part of our works, and some of the sort of considerations and limitations within the VoidSafe system, and then finishing up with some installation considerations. So rather than a technical detail, more what are the practical constraints over some of the details that you may wish to achieve on site. So cracking on then with the first section on supports and fixings. So from a point of view of our deck products, our floor deck products, we have R51+, TR60+, and TR80+. There are shallow floor deck profiles. They can be installed on many different structure types, so frame types, whether it be steel, light gauge. Steel is naturally the most popular, and that is due to the use with composite construction and shear studs that I mentioned earlier, and we're going to look at those details. Is also very popular in light gauge steel frames, so load bearing light gauge frames where the walls go up, and we're going to see a detail on that later. It not necessarily less popular, but less used just because of the benefits that go with it. In a concrete frame, we do see it used on block work, relatively small jobs, but used on block work. And we have also used it on timber frame more recently, as you can see in the bottom right there. So it is flexible in the frames it can be used with. I would say that the majority is used with steel, and that's just because of the added benefits of the two, steel frame and the deck together with composite construction. But probably 20% of what we do, if not slightly more, is on other frame types than hot rolled steel. So it's it's important to realise it can be used on all. And we're going to look at some of those details in a bit. Starting with steel frame, so hot rolled steel. When I say steel frame, I mean hot rolled. So yeah, the first, so non-composite steel beams. So this is a beam not designed to act with the concrete as a composite beam. So in those scenarios, we are using different types of shot-fired fixings than we would use in a composite beam, and we'll come on to that in a moment. So the shot-fired fixing we use there is a Hilti EMP fixing. It has an increased resistance for restraint of the beam, using the deck as lateral restraint to the beams. You can also, in those scenarios, use screw fixings. That would typically not be a preference. The reason being it takes longer. You may have to pre-drill the flange, but it can be used if there's an issue with using sort of live shot on site. Very, very rare now. There used to be concerns with using live shot, but that's kind of gone away now with sort of health and safety and cost assessments, etc. So the standard fixing would be the Hilti EMP on a non-composite beam, just because it's a higher resistance fixing. Then we look at a composite beam, so would have a through deck welded shear stud following the initial fixing to the sheet. In those scenarios, we're using either a shot or gas fired fixing, but it's more of a general purpose nail. So it's smaller, it has a lower resistance. But the key thing I would say about that is the fixings in this scenario. Sorry, I think we've got some feedback. I'm going to attempt to mute other people. That's better. Right, sorry about that. I'm not quite sure. If I can ask people just to check your mics are muted as you come in. I know people that aren't here won't know that, but so yeah, going back to the detail, it's a 50mm bearing still for the decking. However, if you've got through deck welded shear studs, you typically may need to increase that bearing at your edge beam, and I'll come on to why in a moment. But the fixing itself is, as I said, a shot or gas fired nail. It's a less resistant nail than we use on a non-composite beam because you have that welded connection following when the shear stud is welded. The key thing to make sure is that the fixing type and centres do need to be reviewed based on the time of year it's being installed and wind, but we'll come on to that a little bit later. The other consideration around bearings is where you have things that are obstructing the bearing for the deck. So these are some examples. So if you have columns coming off the tops of beams, as you can see here, or where the deck is on the right hand side here, spanning into a column, a large column, then additional support will be required, and it's important that's considered during the steel frame detailing stage to avoid sort of issues at site with site welding, etc. So it is important to look at columns and penetrations through the within the bearings as such, so that you are supporting that deck in the both temporary and final condition. So I talked about the 50mm bearing being the minimum. However, when you've got composite beams, there are minimum dimensions from the center of the shear stud to the edge of the beam, and from the center of the shear stud to the end of the deck. Those minimums are 30mm. So what that does is increase your bearing requirement to 60mm to add the 230 together. What that means is your minimum bearing size at a butt joint is really 120, because you need to stagger those studs, achieve the 30mm minimums in both directions. So you're looking at a 127 being a typical absolute minimum for a composite beam, whereas a non-composite beam with no shear studs, you can go down to the 50mm because for both sides, giving you an 100mm flange width because the minimum limits don't apply. So moving away from steel beam supports, and we're looking around cores or up against walls where we can't sit on the wall, then you would look at an angle support, something like this, on a core wall. A 50mm is the minimum bearing, but in reality, I would say you would really be looking for something to the tune of 75 or above. And the reason for that is to give tolerance in that end. You know, you may have you may have tolerance in the sheet length, and that would obviously limit the installation. So whilst 50 mil is still the minimum, it is recommended to allow some constructional tolerance within that. In terms of sloping, so sloping slabs, decks to falls, ramps, the top flanges would need to be laid to falls in most scenarios. There are situations where we can get away with it without having been laid to falls, but that's on very low degree slopes, and the information you'll find in the TGN on that. The key for this is, particularly if the beams are composite, then you have to lay the beams to falls to get an effective weld for the shear stud through the deck into the beam. As soon as you get a small air gap between the two, like you would get here, you will not be able to get an acceptable weld, or it would be very difficult to get an acceptable weld, potentially with numerous shear stud failures during that process. So important to consider where you've got a slope to think about, and where possible, slope those supports. As I say, there's a lot more information on the angles that we can achieve without with horizontal supports within TGN. And the other thought, and this was actually a question that was raised in one of the CPD registrations for this presentation, was relation to dropping deck down into the webs of beams. So when we drop the deck down into the web of the beam, we still need to be able to adequately fix that deck into place and be able to place the sheet in place. So you can see here the minimum we recommend is 50 millimeters to extend of the lower support, whether that be an angle to the web, or if the deck were to be sat on the bottom flange, to enable us then to get a gun in to fix that sheet physically in place. In addition, that needs to be there to physically be able to put the sheet in place, so in a safe manner. We have seen issues in the past, some years ago now, where it has been intended to install deck onto the bottom flanges of columns. And I think it was only a sort of a very small 203 column or something similar, and you physically couldn't get a long enough sheet between the gap and into to then slide back and get your bearing. So that's why this detail is important. There are other beam types available, but I think there's issues particularly around availability and sometimes cost. So the key thing from an installation of the deck, though, is to be able to fix those sheets in place, because without those fixings, you've got potential for wind uplift, etc. You also have the potential for them to shift off of bearing, which is obviously a huge health and safety issue. So they have to be fixed in place. The only time you can avoid the extension of 50 millimeters is if you have a very deep beam and you're fixing the deck very low within that beam, such that you can get the fixing gun below the flange and above the angle that you're installing onto, or bottom flange that you're installing onto. But a really key consideration where you're looking for the deck to drop a shallow deck into the webs of the beam. So moving away from hot rolled steel, and it was another question actually raised in the CPD registrations. We're looking at light gauge steel frame, and what do we do there? So we sell a fair amount of profile into this sector. So we're talking about load bearing steel frame, light gauge steel frame walls, and this is one of the more common details for that. So we're sat onto a top hat section that's on the top of the steel light gauge wall, and the profile, I would say nearly always used in that sector, not always, but nearly always, is a TR80 plus. The reason for that is it's the longest spanning, and these decks span between two walls, so naturally allow larger spacings for the walls to suit the rooms in the types of buildings that light gauge frame is used. The other thing to note is that we tend to supply into that market crushed end profile, so it's a TR80 plus crushed end, as shown here, and that's what a crushed end looks like. Gives you a better concrete section from a fire point of view around the head of the wall, and also from an installation point of view, you don't need to close the ends of the profile. It goes in with that profile already closed at the ends, and you need to have some tolerance in bearing. That's why there's an optimum bearing of 52.5 mentioned, but in reality, people are typically going up to 60 millimeters because, again, you've got then the construction tolerance allowance there. And then on to masonry support. So on a masonry support, the bearing increases. The bearing increases in accordance with the design standard, but also my thinking around that is that the larger bearing enables that fixing to be placed further away from the face of the wall, so avoiding damage to that support, whether that be concrete or masonry. The fixings we use in this scenario, there are two options. We can drill, plug and screw. Again, slow, can affect program just because you have to pre-drill, etc. Or we also do have a shot-fired fixing available, or a number of different options available from different shot-fired fixing providers that we can use and do use regularly on masonry and concrete crane. Timber is screws only, is what we use, 5.5mm self-drillers. Again, the bearing is 70 millimeters for similar reasons I mentioned on previous, and relatively standard detail than as we see on whether it be concrete, masonry, timber. The kind of detail looks very similar because you don't have all the kind of impacts of the composite beam scenario going on with shear studs, etc. From a point of fixing centres, so fixing centres are similar for all support types. These are our standard recommendations. I'm not going to go through all the numbers, but they're typically increments of near 300 millimeters at the ends of a sheet, so on supports at each end, or every other trough, or 600-ish centres over intermediate supports. That is our standard recommendation. However, as I mentioned earlier, when you're using the lighter fixing on composite beams, you do have to do checks for wind, and there is guidance issued by BCSA upon that, and we do that on every job that we install. So there are not that many, but there are these odd occurrence with specific areas of jobs that may need a slight enhancement, whether that be a better fixing or more enhanced fixing, or closer centres. So, for example, you may install them closer over the intermediate support to provide a greater uplift resistance. But it's something that does need to be considered. Similarly, on high-rise steel frames, they use what are known as mute frames, or deck riders, I think they might also be called, where frames are put onto the deck between the beams with mutes in early in the process, so potentially before it's welded. And in those scenarios, due to restraint for the beams, quite often you may have to enhance the number and type of fixing in those scenarios. And that's something that typically, from our point of view, the steel contractor will let us know, and we will then ultimately install those, because it does depend on the loadings through that mute frame, the beam sizes, etc., etc., to provide the restraint during the construction phase. This is just an image for more than anything from a temporary prop point of view. Temporary prop will be indicated on our drawings. There is a temporary works design required, proper head, typically 100 millimeters, and there's numerous proprietary systems that we would typically use because of the loads involved on long spanning decks. But our design, nearly, I would say 95, if not more % of what we install will be avoiding the need for temporary propping. So we'll be up in the gauge. Steel contractors will be maybe adding a beam in, changing span direction, and all those kind of things. But it's just important to realise that when propping is needed, there's a 100mm bearing, obviously needs to be braced, etc. And the need for that propping will be indicated on the deck contractor's drawing, and it may need to be in place prior to installation, depending on the spans involved. So I think the key thing is avoiding temporary propping where possible, because it sterilises the area below, etc. But just something to think about from a bearing point of view. It is another support type. So that's kind of bearings. Don't think we've got any questions yet, Pete, have we? As such, I haven't seen any.
No, none have come up yet. Which is
Good. Okay. So moving away from the kind of bearing type, now we're looking at slab edges around perimeters and on those supports and what are those limitations. So starting with where the deck would be transverse to an edge, the limit we recommend as a business is 450 millimeters from the edge of the beam. So this is where the deck is spanning out in its strong axis. That means that it can support that distance without the need for any propping or anything on that. Now that limit can actually be extended beyond 450 millimeters, but it depends largely on where the edge protection is. The 450 millimeters is a practical limitation because in reality you've got to get that trim installed on the end of that sheet safely without having to work outside the handrail. So if the handrail is on the centre line of beam, 450 millimeters is kind of arm's length-ish, and it's something that's worked over the years. You can extend that, but in that scenario, you have to then start thinking about where is the handrail? Is the handrail further out? If you had a scaffold at the edge with an extended handrail, so there's a safe way of getting the cantilever further out, then you can extend it further. But that needs to be looked at because as you extend the cantilever, it then comes down to what gauge is the profile, what thickness is the slab to check that it can take the moment over that edge support, which typically it can even up to 600 mil and beyond, but it depends on the specific scenarios. What is your back span adjacent to that edge beam? So that's just an important thing. It can be done, but rarely is because the handrail typically will be close to the edge beam. And that's for that reason. The other thing to note on scenarios like this is the deck will be formwork only out to that edge. So it will need to be designed as a cantilever, a reinforced cantilever. So looking at what mesh you've got in the top, what loads do you have on the edge? If you have a wall line load on that edge, then naturally you're going to need to probably enhance your reinforcement depending on what you've got in already, but you're probably going to have to enhance your mesh or maybe add bars in if you've got a reasonable cantilever for this scenario with a heavy line load, let's say, on the edge. So you'd have to sort of look at that in isolation. Where the deck is in the other orientation, so the deck is spanning parallel to the edge beam, then the maximum limits that we can apply are all down to the thickness of the trim and how far that trim can then cantilever from the support. We do 4 different gauges or thicknesses of trim from 1 to 2 millimeters, and they facilitate up to 200 millimeters from the toe of the beam, depending on your slab depth, as you can see in the table on the right there. There are a number of key parameters, minimum dimensions, but mentioned on here, so you can see the 114 from the center of stud to edge of trim, but that's all related to the composite beam design, and we will facilitate that where possible, but obviously something that needs to be considered in any edge, not just a parallel edge. But there are certain ways of achieving greater dimensions than that, and one way to do that is the introduction of studs. You then have issues potentially with your edge beam, but what that does enable you to do is take the deck right out to effectively the slab edge, with a trim tacked on the side. So you effectively got the composite deck spanning along your slab edge. But you then look at seeing where those stubs are needed, can you put them in, etc. But it is a way of achieving quite a large cantilever compared to an edge trim alone. This is more just to indicate things we also offer. We also do offer channel edge trim. We don't manufacture ourselves. We used a number of approved suppliers that we use, and we would detail and supply that. The edge limits are slightly different, and that's largely due to the weight in the channel, but that's obviously all guidance, and it does vary from supplier to supplier, but it's something we will look at in our design and then determine whether any edges would need propping to those edge trims. Just thinking about tolerances of trim. So we've seen the kind of edge positions that we say are the maximums, but then when we've got a dimension, how accurate are we installing that? So you'll see in the top right there, that image is straight out of the National Steelwork specification. So it's plus or minus 10 millimeters, but that will be from center of beam because that's the physical point that we're installing a trim to. So there is obviously a tolerance within that at site level. If, as we do sometimes need to, you have a curved trim, which you see in the image on the left, then that tolerance is increased by the nature you've got facets around it, so that increases your 10 millimeters. And our tolerance for that is plus or minus 25 from the effective curve. So just key things to think about. One thing to be aware of, and we do have to do this on some jobs, is the tolerance is important from an intended grid line and not from the beam edge beam position, which will already have its tolerance from a grid line. Is that we can also install to engineered positions. So once the beams are installed, the deck is installed, an engineer will then go round, see where the theoretical grid lines should be, and we can then do measurements from there to ensure that you're reducing the tolerances involved and not ending up with a compound tolerance of the beam and the edge trim. But that's only where that kind of edge position is really critical for maybe the facade that's being installed or whatever. Just a detail that we offer around upstands, and something that is relatively common, particularly with now we offer concrete and of upstands as well, is a higher edge trim with more restraint straps to form that upstand to the perimeter. Typically, that would then the slab will be poured to level, the standard slab thickness, and then we will be pouring the upstand as a separate operation, obviously with traditional formwork on the inside, but the trim forming the outside, taking away the need of any additional sort of support around the outside for traditional formwork. Toe boards kind of moved away from this now. We don't tend to do it so much anymore because most handrails will now have an integrated toe board. But in the past we do still offer, but we did it a lot more in the past, a toe board installed on top of our trim that was then easily removed on site by just knocking the heads of the screws off and removing the toe board. Something that we can still offer, but as I said, it's rarely used now due to the system edge protections that are now available and the fact they have integrated toe boards, etc. It's moved on quite a bit. One detail over steps in slabs that I thought worth mentioning is the thought about whether you have a trim or not at step in slab. And really the key thing from our point of view there is if you have a trim in a step in slab like this, so you can see we have an edge trim on the edge of the beam here, then that enables that whole area, upper and lower slab, to be poured in one process. The cost of a concrete pour is largely in the pump and kind of the commissioning of the pour on the day. So to be able to pour two levels at the same time could be key if those upper and lower slabs are quite small, so you're able to pour the two together. In a scenario where you have continuity like this, you have to pour the lower slab, put something in place on top of the lower slab from a formwork point of view to then pour the upper slab. So that's a two-stage process, which naturally has cost and program implications because it would be over 2 days. You'd have to mobilize a crew for 2 days, etc. If they're both large slabs, the issue goes away because you're probably only going to be able to pour the lower slab in one day and then the upper slab. But if it's two smaller areas, then it's definitely worth thinking about how you achieve that upper level formwork and whether you do that in an edge trim.
Hi, Jamie, I've just got interrupted you. We've got a couple of questions, really. A couple
Okay.
regarding crushed ends. Bob's asked, do we see the use of crushed ends becoming more popular in standard steel frame construction? He says that they have seen it recently. And also Jay has asked, does crushed ends have any effect on the composite performance of the slab itself?
So I'll take there's two. The first one, do we see it used on hot rolled frames, so not light gauge? Yes is the answer. I would say largely that is in jobs where you've got pre-studded beams, because then with pre-studded beams you naturally have single span sheets. So particularly in car parks, anything where you've got an aggressive environment, so you're pre-studding the beams, painting them or galvanizing them or whatever. So then we would get single span sheets, and then naturally you'd want the crushed ends because it makes firstly closes the ends. You don't have to put end caps on, makes the installation quicker. It isn't used so much in what I'd call a standard job. So a standard job, what I mean by that is loads and loads of spans where you're double spanning sheets, they're butting up against each other. Crushed ends doesn't tend to be used there because it doesn't need to be, I think would be the reason, because you'd be crushing stuff where it can butt anyway. Crushing comes at a premium because it's another process, and you'd only really need to crush the edges of the building in that scenario. And by the nature of making crushed ends, you're crushing both ends of the sheet. So it's not it couldn't be used. Sorry, I'm just going to mute whoever's mic that is. Crushing, it's not that crushing couldn't be used in a traditional double span sheet job, but we don't see it used that much, and I think that is because of cost premium, but also there's not really a need for it, and you can end cap the edges. But yeah, certainly see it in anything that's anything that's pre-studded, anything that's single span. So where we were looking at the angle supports, it dropped into the angles. A really good reason to use crushed ends. So yeah, that's that one. In terms of the composite performance, and I'm not sure whether the question means composite slab or composite beam, but in both scenarios, the answer would be yes, it does improve it, because in a composite slab scenario, it creates an anchorage point at the end of the slab because you've got a crush and then the concrete going around it. And in the shear stud scenario, where you have studs, particularly like in a pre-stud scenario, you naturally get more concrete around that shear stud. I say that, however, we haven't done testing or shear stud testing with crushed ends in that scenario, but you could. There's certain sort of engineering judgment you can make depending on where the crush is, depending on where the stud is, and depending on the dimensions between the two. But in terms of the composite slab performance, again, we haven't tested it specifically with crushed ends. Whilst it will give it an enhancement, we haven't tested it because typically that's not the governing factor. The governing factor is more often than not the construction stage. So the answer is yes, it would give a benefit, but until the kind of design needs that benefit, then it's not necessarily needed to test the size of that benefit, if that makes sense. Hopefully that helps. And if there's more questions, then please do add them, and we can touch back upon that.
Before we move on, Jamie, there is one more question from Daniel. Just asking, could trim be installed before the decking is in place on the beam? If it is safer, is it safer to do it that way?
I would say yes, it could be installed before, but I wouldn't say it's safer, because obviously you install the deck and that creates your platform to install your trim. You could install trims on the beams before, but I think that would probably create some difficulties, because at the end of the day you've got closure and trims around columns, and I'm assuming he means before the beam even goes up to level, because if not, if you're thinking about installing the trim to the beam once the beam is in situ in its final condition, but you then got the access of how do you get up there? Do you have to do it from a mute? How safe is that, etc. The other thought, in terms of if you install the trim on the floor onto the beam and then lift it, is will the trim get damaged in lifting the beam to level with chains, etc., depending on how it's being lifted. So it could be done. It's not typically what we have done in the past is built small modules on the floor, where kind of working at the edge on really high-rise buildings was a problem. Some years ago now, we built like modules with actually deck and trim on that were then bolted onto the edge of the building. Not common. It's quite complex to do that, because you're then having to do a lot of the connections at floor level. That can be done, but I think for what I'd call a standard job, then doing the trim from the deck once it's installed, because you've got that deck working platform and most of the trim is within I'd say 200 mil of the edge beam, it doesn't create a problem, and we tether that trim during installation anyway, so it kind of reduces most of the risk. Okay, hopefully that helps. So on to now shear studs and flashing, so moving away from edges but into the floor plate of the deck. So from a shear stud point of view, the shear stud centers are governed by the deck orientation and the geometry of our product or the product you're using. So this is just two examples. There's loads of information in the link on the bottom left. So our R51 Plus on the left-hand side facilitates studs at 150 across its profile. Our TR Plus profiles facilitate 333 on our TR60 Plus and 300 centers on our TR80 Plus. So naturally that influences where you can put a shear stud, and the minimum beam sizes are governed by code limits, which we'll look at. One thing that can and is often an issue is studs when you have raking beams. So we try to sort of display it here. There are frame design softwares that permit, or typically frame design softwares permit standard spacing. So with a TR60 Plus, they'll permit 333 spacings on perpendicular beams, and they'll permit a standard spacing on a parallel beam that is chosen. So you can govern the standard spacing because it's not limited on a parallel beam. The issue that causes is you do get some beams that are raking where it will try and put on one per trough. So to use the example up here, it will try and put one at 333 centers on this raking beam when the deck is spanning this direction. That isn't possible because you'd end up with this scenario where you're trying to weld studs through different parts of the profile. So to achieve a number required, you are having to double some studs up. However, doubling studs up doesn't give you necessarily the same resistance as a single stud. So you then have to start looking at how close together are the studs, etc. Because the closer the studs are together, they are closer to acting as one because the cone of concrete failure overlaps more and more. So it's important to think about this when designing composite beams, because the number of studs that are achievable on that beam is governed by the angle that the rake is in relation to the product. One thing to mention, I mean, this is shown very much on a TR60 Plus profile, but one thing I always encourage is if you have a lot of raking beams and you're looking to design them as composite, then R51 Plus is by far the best profile to use, largely because it has the greatest flat area on the product. So if we go back a slide, you can see there's a lot of flat area. It permits studs every 150. So with a raking beam, you still have a large amount of flat area to put shear studs onto the beam. With the trapezoidal, obviously the raking beam just creates a larger voided area, which causes the problems of potentially getting the number of studs that your composite beam design software has required. So just a key thing on raking beams, and there's loads of stuff in TGN on that now. It's something we've recently added, as we do see it from time to time. I mentioned about product influence, so it's not just about the geometry and the ribs, but also the width of the profile. Where you have parallel beams, depending on how that deck will sit on the beam, you have to think about how we can then weld a stud to it. So we do that by the use of different flashings. The primary beam spacings obviously influence this, and in an ideal scenario, you'd influence your primary beam spacing to suit the deck profile. Appreciating that's very rarely possible due to other constraints in the building design, but we do it by flashing. So we'll be using Z's at edges, or we might use an angle closure where we're having to cut a sheet away to install the studs onto the top flange. These are shown as edge beams, but we might well do the same in the middle of a floor plate as well. And I mentioned earlier about pre-studded beams. So this is to give an importance of pre-studded beams and setting out of the decking and the pre-studding. So it's important to integrate the two. So we will detail on a pre-studded job, we will detail the decking and we will advise where the studs need to start. Because when you're installing, you want the studs lining through with the flat area of the profile, particularly where the beams are narrow, to maximize the concrete area that's going around these shear studs. If you don't do that, this is what can happen. And you can end up with a stud not lining through. So naturally, whilst you've designed that based on the code stud resistances, that doesn't have the concrete cone around it that will necessarily mobilize the stud resistance intended by the code. So it's important to integrate the two. We will always do that on jobs that we do. We send a drawing out that has stud setting out, or not at least deck setting out, so the fabricator will know where to start the studs. The other thing that I mentioned slightly earlier, or in answer to a question, is to use crushed ends in a scenario like this. Obviously creates you a lot better way of justifying that stud resistance, because you do then end up with a larger concrete section, and you can potentially look at that beam differently depending on what the flange width is and depending where your deck bearings are and the crushers are. But you potentially have a wider concrete section that is then solid down the center of the beam. So it's something that can be looked at, but the important thing is just to coordinate the two. There are so when I mentioned about the code uses spacings and the design resistances are based on spacings. These are some of the more standard ones, just straight out of the code. Again, this is all online. It's in the standards anyway. But one thing I'd bring the attention to here is this rule at the bottom right. So the flange thickness that is stipulated in the code is it must be 0.4 times the diameter of the stud, which is 7.6 for the typical 19mm diameter shear stud. Now, that limit is there to ensure you can achieve an effective weld. However, very thin flanges above 7.6mm, when used with coatings, intumescent coatings, paint coatings, because they're so thin and the stud welding process involves heat, you can get issues with damage to the underside of the coating. So you can see here two examples, one where the heat has caused damage to the paint, one where it's actually reacted with the intumescent coating, and you can see some kind of raised areas in the beam. So while 7.6 is the absolute minimum in the code, and you might at 8mm, okay, I've met the code requirement, it may not be a practical, it may not meet the practical need, because you end up with issues such as this. So it's important. We rarely get down to that thickness of flange, but it can have an influence. So it's just to be careful, depending on what the coatings you've got to your beams, and that their potential for touch up will be needed afterwards. Not strictly related to studs, but more flashings. We are now in a situation where we are trying to minimize waste and cutting at all points. In the past, sheets may go in, and just where they needed to be cut, they would be cut. We are now doing it to minimize waste by utilizing flashings and to avoid as much cutting and wastage that needs to be removed from level as possible, sorry, scrap from level as possible. So we do that by setting out with flashings and looking at optimizing the layout of deck on the floor. It reduces the amount of cutting on site, it reduces the program because you don't end up with loads of cutting, it reduces noise and naturally reduces wastage of material, which is obviously key for a sustainable world. And in doing that, sorry,
Karen, if you like. Just asked a question regarding problems with thin flanges, or some, the depth of flanges, and fixings. Have we ever found that, like, if you shot fire fixings, will they damage the underside of the flange, or have we ever had anything like that, especially with screws, I guess?
Well, on a very thin flange, I would suggest the more robust nail. I can't think of an instance where it's necessarily been raised, not with floor decks, but if you just think about the size of the nail and the thickness of the flange, there is potential, because when a shot fired nail is installed, it obviously displaces steel as the nail goes into the beam, and on a very thin flange there is potential, particularly I would suggest maybe with an EMP, that you would, depending how critical it is, but you would potentially see very small dimples where those fixings are located above. I'm not aware of an issue, and I'm looking at my colleague who's sitting opposite me to see if he is, but no, he's shaking his head. So I'm not aware of an issue, but there is potential for it to show through. It wouldn't It wouldn't pierce through, but you might see a small displacement. I'm talking on very thin flanges.
I think what Bob's asking is, can it damage the coating? I don't know if Bob's had any instances where it's happened to him.
I wouldn't say it couldn't. I wouldn't say it couldn't. It comes down to the thickness of the flange again, I think, because it's displacing steel. Obviously, the thicker the flange, the less effect it will have on the underside of the flange. I wouldn't say it couldn't, but it's not something that I'm aware of myself in my experience, which is quite a long time. I'm getting older. So yeah.
David Marshall has also asked, what's the minimum top flange thickness you would recommend to avoid impacts on instrumentation?
Ooh, that's a dangerous one. I'll pass on that one and come back to it. I'll answer that directly. I'll have to have a look. To be honest, I'd have to have a look at a few jobs where we've had issues to see what thicknesses they are.
Settings also. There's the stud welder puts stud welding system in there, and
it does. It depends. It depends largely on the flange thickness is naturally going to protect you against the issue. The thicker the flange, I'd need to have a look at some examples because it does come down to the climatic conditions on the day, the weld settings the welder's having to use, what ampage he's having to use, and what timing he's having to use for that weld. Because the longer the time and the higher the ampage, the more it'll impact the steel.
Can I just interject? It's Bob from Sherwin-Williams here.
Hi, Bob.
Hi, mate. From our experience, if there is heat damage, if there's you get like a brittle bubble, don't you, underneath on the underside of the top flange. So if those are left intact, then you've not got a problem. The issue is when they're damaged. Natural reaction is to stick your finger in and break the bubble.
Oh, right, yeah.
And if that's the case, then they do need repair. But with an intumescent coating, certainly with our intumescent coatings anyway, if you leave them alone, you're okay.
Right, yeah, because you've still got the seal on it as such.
Yeah, and you can have problems with this penetrating nail, where the nail can, if it's pre-installed fire protection, if the fire protection has gone brittle, then that nail can actually cause damage to the intumescent. That was the purpose.
And I guess that comes probably. I would suggest that probably comes more on non-composite beams because you're using a heavier nail and you potentially got a thinner flange because you can get away with it because you haven't got welded studs.
That's it. That's why I asked the question about the crushed ends.
Right. Yeah. Okay. No, thanks for that, Bob. To answer the minimum flange thickness, I would recommend I go away and have a look at some examples. So at least I'm basing it on some reasonable evidence rather than me to put a finger in the air. But obviously, Pete, you can give me those details and we can follow that up afterwards from the technical help desk after looking back at some of the examples. So yeah, minimising wastage I mentioned. So we're talking about flashings. We've already done that. But that has led us on to develop other flashings. We've developed one we call FT. It's essentially a small trapezoid edge flashing to stiffen the flashing at the edge. You can see an image of it there. It's press brake flashing. We've developed that with SEI have developed that on our behalf. And we worked with them to determine the kind of safe distances that could be used. And it's been successful. It's not needed on every job by no means, because you can usually get away with relatively small ones. But what it's doing is then trying to avoid unnecessary wastage, cutting at height. So you can see it used in an example here at the very edge of a beam. It's enabling you to span slightly further along that very edge perimeter. And in addition to that, it allows you to, this is just to try and show what we mean, but only with one sheet in the middle, you can shuffle the sheets around to look at what you can do on either side of the decks. It's something we use internally when we're setting out decks to maximize coverage of the deck and minimize wastage in material and minimize working at height, site cutting, and all the HAVs concerns that go with that. So mindful of time, we're on to voids and VoidSafe. This is a relatively quick one. I'm mindful this was in for an hour. So void rules, these are standard. They've been the same for a long time. They're available online in the bottom left section. They're categorized essentially into 3 types of voids. Small voids, the limit, as you can see on the screen, requires no special treatment. Medium voids you would need to know about early because you have to design additional reinforcement around them. So that's up to 700 mil, and anything greater than 700 mil, we would typically want to see structural trim in steelwork because we would then be forming them with trim. And this is standard, this is SMD guidance, and it's very similar across the industry. The reinforcement for medium voids, it's beam strips around the voids. There's some really good guidance in SCI publication P300, and this is just an image we've put together, but the principles of that information in this are similar. So you're adding bars in to create reinforced concrete beam strips around that void. But clearly you need to know where that void is and design the reinforcement before pouring, and often voids are a late client requirement. So a late client requirement for a large void is going to need supports below, so beam supports underneath the deck. In terms of VoidSafe, VoidSafe is our GRP grating solution that we've tested and integrated with a specific VoidSafe trim. You can see here, it's just an example of it. So it covers the void during installation. So we will install that whilst the nets are still in place. We'll install the deck, the trim, the VoidSafe. Then we can remove the nets because it's safe to be walked on. And then ultimately in the final condition, when the concrete is poured, it's protecting the void for the life of that building. And there are rules allowing cutting through the VoidSafe up to certain sizes, or we also have the proprietary solution where you can add additional framing from above to support around those voids. We've only recently released that called Void Beam, and it is basically a top hung solution to support the grating. This is a section through, and the trim, what I would hasten to add is the VoidSafe trim has different limits from standard trim, because you obviously have a load during the construction phase of the grating and potentially people on the grating, as well as the concrete as it's being poured. We've developed the rules for that, again, with help from our friends at SCI, and that is since the information for that is all on TGN, and the limits for VoidSafe trim. You can see it's principally a recessed edge trim with a safety platform on top of, which is a non-slip GRP grating. There are some considerations that you need to think about in terms of edge dimensions that impacts on, and specifically where you have composite beams. So around those perimeters where you've got composite beams at the edge, you need to be able to get your shear stud in. So that naturally increases the dimension you need from the inside of the beam to the edge of the slab, because you've got to be able to achieve, if it's a pair, the distance between the pair, but then also enough access to get the very edge stud in. So that 75 millimeters that you see there is access to be able to install the stud in place. So these are just rules that apply where you have a VoidSafe trim, because it's more onerous than a standard trim due to the 55 mil recess for the bearing. And that is that section finished. So we're going to finish up now. A lot of these have been more about technical details. These are now more practical considerations. So you'll see what I mean when I say that by the fact you see loads of fixing tools on the screen. So one key thing from a practical limitation is obstructions above, ensuring we can fix in place. So we talked about it when we were looking at angles drop down in the beams, but it also applies whether you've got an obstruction above. So you may have a step in level where you've got a beam over a beam, and you need minimum dimensions to safely fix the deck in place. Although we do have options where we could tech screw on a particular beam, so that would reduce your clearance required. But it's important to know this, and probably the most important one of all is the welding gun clearance, because if you've designed a bottom beam in a step like this to be composite, that it needs shear studs, and you can't get the gun in, you can't weld the shear studs, so you then have to find a way on site of welding those studs, not using the traditional through deck welded shear stud approach. So they would need to be welded by the fabricator, which means mobilizing different works that potentially weren't planned, etc. So in that scenario, you're probably better off designing the lower beam as non-composite to avoid it. You could pre-stud that beam in the shop, or just ensure that the gap between the two is adequate for the shear stud gun. And that's shown better in this example. So you've got to be able to make sure we can get those studs in below. The clearance is 450 plus stud. So in a standard 100mm nominal stud, you were looking at 550 millimeters. And yeah, just a practical limitation, because the last thing you want to do is have a composite beam that you can't put studs on when you get to site. End caps or crushed ends. So we mentioned crushed ends earlier, and the question kind of alluded to when would you use it, why would you use it, and do we see it used more? So you could use a crushed end in this scenario. This would be this is just an edge, but if the other end is a butt joint, you only need the crush at one end. But crushes are naturally at both ends of the profile just by the way it's made. So you'd be using a lot of crushes for no reason. So perimeter edges where it's only the perimeter is typically end cap like this. But this is a top hat section like we saw in that detail. The crushed end, you can see the very small construction tolerance we were talking about. But that kind of explains or displays really where they come into their own. They also come into their own, as I mentioned, on pre-studded beams, which is where we see in car parks and the like. And they're something like that. So you can see there, pre-studded beam, everything single span, long runs of it. If you had to go along and put end caps on all of these, it would be firstly a longer program, and secondly painful, and thirdly you wouldn't get as good kind of reducing grout loss. So end caps allow potential for grout loss through more than a crushed end, and the crushed end is effectively a seal to the edge or the end of the profile. Last couple of things: construction joints, whereabouts we position them. The guidance is in our TGN as with everything else, but we would typically say no more than a third away from the beam, ideally at the end of a sheet, so that you're not impacting on deflection within the sheet. And if you're positioning it over or close to a beam, then away from the line of studs, such that you're not creating a potential for less sound concrete around the shear stud itself. So whether that be slightly before or after the shear stud, but ensuring that you're not impacting on the kind of cone of concrete around the stud. Bit on crane voids, because it's something that people do ask. We have to return to do crane voids because cranes, obviously the tower crane will come out late in the process. So we typically would install a reversed edge trim that creates a bit of a closure to anything going beyond that trim. But we would want to see a day join or stop end back from the edge beam, such that it then enables you to get shear studs and everything onto that edge beam. So to give an example, with the crane in, we've got back to front trim as we saw already on there. You'd then net it, the handrail would be removed. We'd then take that trim off, deck it, and you can see from one to the other, you can't necessarily always get the studs onto around the edge of your crane void. So it may be at that return point that we're having to stud weld, hence the reason for stop ending back from the very edge of a crane void. And then ultimately that last bit would be another concrete pour to close it off. Just a detail, we offer service fixings for all our products. These are Lindapter are the typical people we recommend. There's a V-nut for the R51, although there are others options available. And the one for our TR Plus profiles is called a TR60 wedge, is the name of it. And you can see how it operates there. Information, contact details, etc. You will find that all in section 13.8 of TGN.
So Jamie, I think we've had quite a few questions actually.
Okay.
During that part.
Okay, that was me done. So any questions? So that's right on cue. Yeah, go ahead.
Daniel's asked for when pouring wet concrete, about propping, but it's preferred to increase the gauge rather than use propping.
Correct. Correct. Yeah.
And why would you say that? I think we've had a few responses to it as well, actually saying.
Why would I agree with it?
Yes. Yeah.
Well, the main reason is avoiding propping. Is it does, if you've got to have prop in place, it's just another process that you have to do on site. That propping interrupts the area below the deck, so that propping has to be in place for a period until the concrete is cured. So it kind of sterilizes that area below. It creates an obstruction. When you've got multi-story buildings, depending on the capacity for the floor below to support the propping, it may result in you having to prop all the way back down the building, depending on the capacity of the slab below to take the load that prop is having to support. So that would be my main reason. And if an increased gauge can avoid that, then the cost of an increased gauge would be far less than the cost of a temporary works design, getting propping in, getting props on site, etc. That would be my feeling. But yeah, I don't know if you say other people have commented, then hopefully they've said the same as me.
Yeah, Jay said something similar to you. He said that it seems he's explained his reasons for it and almost echoed what you just said actually. Jay's also asked there are solutions for shear studs, alternative options. Hilti HVBs being one. Although he's not sure of clearance you would need for that. I've shared the link to the TGN section on that. But did you want to just go over the HVBs at all?
Sorry, I'm just catching up with where you're saying, just so I can see. Yeah, so there are other options available. You're quite right. Hilti HVBs are an option. They are a cleat that is shot fired onto the beam rather than welded. So there's clear benefits in terms of no welding rig, etc. Power requirements for that. You can do it at the same stage as the deck. However, they give a lot lower shear resistance than a shear stud. Hence, you then need more of them compared to a standard shear stud. And also, they are more costly. So that's not necessarily a reason not to use them. If you have small numbers, and it's actually something we've recently implemented within some of our contract teams, if you have small numbers of shear studs, then HVBs are potentially a viable option. If you have an area where you maybe can't get a welding rig to, or you can't get power to weld to, then HVBs are certainly an option. Or at instances above, I'll tell you where we used a lot of them was in many years ago. Tesco's did a program of 2-floor trading where they built new levels inside their stores, and we were obviously then fixing over a live store, which meant you couldn't weld above that because potential for sparks, fire, etc. So we used HVBs there. So there's certainly option. They are an option available. They have a place. Right now, I don't think potentially they are for the mass market big high-rise jobs, but they're certainly worth considering in where there's logistical challenges for welding and also where there's small numbers required. That would be there's actually also other options than HVBs. There's another company that make them called Technaria, but for really similar reasons as the HVB. They can be used with our product, but for similar reasons they don't tend to be because of cost and time to install. But small numbers, definitely a place for them, and we do them.
We've had a couple of other questions. Brian's asked regarding VoidSafe. What gauge edge trim do you use to purpose the folded trim that supports the GRP? I believe it's 2 mil, isn't it?
I was going to say it's all 2 mil, I believe. Yeah, I can't remember off the top of my head, to be honest. But yeah, I'm pretty sure it's all 2 mil.
We've also had one. We've had multiple attendees. Email list. Oh, okay, yeah, that's fine.
I was sending it. Yeah, okay. You've answered the attendance certificate. Hopefully that's covered all of them. I'm just scanning through. I think most of them people have answered or we've answered, which is good. It's been good that we have had some sort of conversation day questions, which is good. I hope everyone's found it useful. If you have any questions after this, presentation, then by all means you can get in touch with us. We have a technical help desk, which is a phone line, but you can email us at technical@smdltd.co.uk. And yeah, follow us on social media, LinkedIn primarily. That's where Pete will typically share all the events like this. That's right, isn't it, Pete? Generally LinkedIn, but you do use other platforms.
LinkedIn, we're Facebook. We'll also send everyone an email reminder of each event that happens. So as they happen, you'll all be notified.
Yeah. So thanks everyone for listening. I'll stop on for a couple of minutes in case anyone else got any final questions, but otherwise have a good lunch and rest of your day. Thank you. I'm going to hide my camera now, Pete, but I'll stop here just in case we have questions.
Yeah, it's fine.